And I should be live, right? What's up, guys? And I know it's been a while since I streamed. What happened was, well, I had my practicals. So I went to the university, stayed in Delhi for a while, spent my week there, and wasn't really able to stream because of that. And I got back yesterday. Well, I got back pretty late, I think around 7 or 8 p.m. And then, am I not in the center? Doesn't matter. Right. And then I was very tired, had an interview, gave that, went pretty well. Well, I'm not sure, we'll see. And it's been a while since I touched DSM. I've been solving problems of the days, problem of the day on LeetCode for like whenever it's something I can do. And I was able to solve like three or four, and that's pretty good for me because these are random questions that I can solve. One of them was actually a question that has been repeated, so that's nice. That's something new. Someone's on stream. I look dead. I do, right? And it's weird. I'm gonna sleep at 45. I'm just gonna stream for an hour. That's what I was thinking. And then we can close this. So let me just share my screen. But it's been a little hectic, honestly, and I gotta start grinding again now. So that's what I'm gonna do. What's this called? Right, close this off. Uh-huh. Leet code. Just spent a couple of my days. Wait, is it? It's Wednesday. You guys wanna do one Google away question? We can try doing that. Given an integer randoms of window size k, return a list of averages for each sliding window of size as the window moves. When calculating average, ignore largest k numbers within that window. The largest k numbers within that window, use a priority for that. Right, just a priority question. Window size equal to 3. Right, k equal to 1. Largest number 30, largest number 40, ignore. Largest number 5, ignore it. Pick your poison, something. What you doing? I think what we can do is we can use a priority queue. So where's my, okay, I don't have VS Code open. Right, got it now. Ring namespace. I'm doing something wrong, aren't I? Right. You include the IO stream. 15 subs, by the way. Yeah, I was kind of thinking about that. Was it less? Was it less? No, I think that's right. Let me just check quickly. And my pinky hurts because there's a hangnail that I tore off. Did it work? It did work, and it took 18 seconds for it to work, which is abysmal. Why would it do that initially? That's weird. Anyways, right. So what we don't want to do is we want to create a function that returns us an array output. So it's going to be a vector and averages. It's going to take in a vector and nums int window size int k, right? Integer k, window size, nums, right? So we need to ignore the largest k numbers within that window. 11, right? So I got more subscribers within the last few days. That's really nice. I had no idea this was happening. Someone's going behind my back and subscribing to my channel. That's not okay. Need to find out who that is. I didn't even get a notification. Like usually I do get a notification that someone subscribed. Which didn't. Right. So what are you supposed to do in this question? You're supposed to ignore the largest element, right? But the largest element can change, but can't change by a lot. So suppose in this, the largest element is here, we ignore that. Then we pop this out, get this in. Creating it is log n. Creating a priority queue is log n. So we got a window size of k. You need to ignore the largest k. You got a window size and you need to ignore the largest k elements. Hey, that's really interesting. How would I do this? Let's take this as an example. I'm just gonna copy this entire thing. Right, make this black. And now what we're gonna do is 51387 window size equal to k equal to 0. So that's the window size I've got for now. 51 k equal to 0. You don't ignore anyone. That's dumb. Then I'm gonna use this example. Right, window size equal to 3. So you've got this, right, added to a priority queue, and it's gonna be maxi because I want these at the top. So that's 30, and then it's better on a trackpad, like these drawings, better on a trackpad. 30, 20, 10, got that, and then you pop the top one out. Like replace these, delete it. And then you empty the priority queue. Do you? I don't think you do. I think you can recurse through like each element and just get an average. But now what you want to do is when you go here, you add a new element, you take the old one out. How do you take the old one out? That's the question. That is the big question. How do you take the old one out? Hmm. If I create a new priority queue for like each time, then wait, heapify complexity. I got some blue lens specs. You did. I should wear my specs. Thanks for reminding me. It's really nice that you did. It's got a linear time complexity. So creating a new priority queue takes a linear time. It's gonna be 1, 2, 3, 4, 3, 4, 6. That's 6 minus 3 plus 1. So my time complexity is gonna be n minus window size into k. No, not k. Oh man, so nice. So what does a nice solution for this look like? Let's try with that. Nice solution, simple. You get these elements, then you sort them, and then you just get the first few elements, right? You move on. So that's 1, 2, 3, 4, basically n minus window size into how much time does sorting take? Takes n log n, right? So that's k log k. That's basically n into k log k. And then calculating average is just, it's not really time taking. It is though. You gotta loop through each value. K log k, and then window size minus k. So it's n into k log k. Each time k log k happens, that is you sort. What you gotta do is you gotta multiply that with size minus k. Mm-hmm. Right. How would you do that? Each sliding window. So I know there is a question of median. Oh, interesting question. I need some help. You guys not getting any interview calls. What? Anyways, what we're gonna do is we're gonna look at source codes for a few data structures, and I also went ahead and learned binary search trees because, well, I felt like it in the moment. I also did watch the traversals, but we can watch that again. We can look at the code, and I'm really interested in what hashing does, how it actually works. I'm really interested in that. What the fuck are Fenwick trees, bro? I just want to do hashing for now. Let's just do hashing. Right. I'll mute myself and we can watch this together, right?
All right, welcome everybody. Today we're going to be talking about hash tables, one of the most remarkable data structures of all times. If I had a subtitle, it would be One Data Structure to Rule Them All. So let's get started. There's going to be a lot of things to cover in the hash table series. We're going to start off with what is a hash table and what the heck is a hash function and why do we need one. Then we're going to talk about some popular collision resolution methods, in particular separate chaining, open addressing. Those are the two most popular ones, although there's a ton more. Then we're going to separate chaining with linked list just because it's a really popular implementation. And there's a ton of stuff in open addressing that needs to get covered. So we're going to be talking about linear probing and quadratic probing, how that's done. I'm going to be giving lots and lots of examples for those just because it's not super obvious how they work. And to finish off, we're going to be going over double hashing and finally removing elements from the open addressing scheme because that's not so obvious either. All right. So to begin with, what is a hash table? So the hash table is a data structure that lets us construct a mapping from some keys to some values via a technique called hashing, which we'll talk about shortly. So the key could be any value as long as it's unique, which maps to a value. So for instance, keys could be names, which are people names, and the value could be someone's favorite color. So William's favorite color is green, Micah's is purple, Catherine's is yellow, and so on. And we call these key value pairs. So each key is associated with a value. So all of the keys have to be unique, the values don't have to be unique. For example, Micah's favorite color is purple, but also Leah's favorite color is purple. We often use hash tables to track item frequencies. For example, below is a frequency table of the number of times a certain word appeared in Shakespeare's Hamlet, which I parsed and obtained this table. So you can see Hamlet appeared 114 times, the word Lord 223, but the word cabbage did not appear. So hash tables are often used as to track frequencies, which is really handy. But you can really construct a mapping between any key value pairs, given that the keys are hashable. This is something we're going to talk about shortly. So to be able to understand how we construct the mapping within a hash table, we need to understand what a hash function is. So simply put, a hash function, which I will denote from now on as h of x for some key x, is a function that maps x to a whole number in some fixed range. That's pretty simple. Let's have a look at an arbitrary hash function. So if our hash function is h of x equals some polynomial x squared minus 6x plus 9 modulo 10, well, all the integer keys get mapped to the range 0 to 9 inclusive, no matter what integer number I plug into h of x. So below, I'm plugging in certain values, or keys, if you will, into the hash function and getting an output. So notice that the output is not unique in that there could be two values that I plug into the hash function which yield the same value. For instance, h of 4 and h of 2 map to the same thing, and that's completely fine. So we can also define arbitrary hash functions, range 0 to 9 inclusive. Some polynomial x squared minus 6x plus 9 modulo 10, well, all the integer keys get mapped to the range 0 to 9 inclusive, no matter what integer number I plug. We need to understand what a hash function is. So simply put, a hash function, which I will denote from now on as h of x for some key x, is a function that maps x to a whole number in some fixed range. That's pretty simple. Let's have a look at an arbitrary hash function. So if our hash function is h of x equals some polynomial x squared minus 6x plus 9 modulo 10, well, all the integer keys get mapped to the range 0 to 9 inclusive, no matter what integer number I plug into h of x. So below, I'm plugging in certain values, or keys, if you will, into the hash function and getting an output. So notice that the output is not unique in that there could be two values I plug into the hash function which yield the same value. For instance, h of 4 and h of 2 map to the same thing, and that's completely fine. So we can also define arbitrary hash functions, not just on integers, but on arbitrary objects, which makes this really powerful. For instance, suppose we have a string s, and we're going to say h of s be the hash function that I've defined below. So this hash function, all it does is it sums the ASCII values of the characters within a string, and then at the end says modulo 50. So that will, for any given string, just output a number, and that's a hash function. So for example, some simple inputs. So h of bb gets 66 plus 66, and then we mod that by 50, so we get 32. The empty string gets 0 because we don't even execute the loop, and so on. So we've effectively converted a string to a number. Great. All right, here's a mini challenge for you. Suppose we have a database of people below. And each person has three fields. They have an age, a name, and a sex. I want you to define a hash function, h of a person, where you're going to be given a person object as an argument. And I want you to create a hash function that's going to map a person to the set of values 0 through 5 inclusive. You can pause the video, just create any hash function that does this given the three fields. All right, so here's my attempt at creating such a hash function. Turns out there was an infinite amount of possible hash functions we could define for the hash of the person. And here's a simple one. So I'm going to say, okay, first let's start with the age. So whatever there is, that's the starting value for the hash. Then I'm going to add on the length of the person's name, again, an arbitrary choice. And I'm going to increment by 1 if they're males, and then mod by 6. So as you can see, hash functions are a bit arbitrarily defined at this point. We're going to get into some more sophisticated hash functions later. So this particular hash function yields those values. All right, something very important, very, very important we need to talk about are properties of hash functions. So if we have a hash function and two objects, say x and y, and their hash values are equal, then those two objects might be equal. We don't know for sure. We have to explicitly check x against y, because the hash function tells us that there was a collision right there. But if the hash functions are not equal, then x and y are certainly not equal. Here's a good question. How can we use this to our advantage to speed up object comparisons? The answer is that instead of comparing x and y directly, if we've already computed their hash values, then first let's compare the hash values of x and y instead of comparing x and y explicitly. In this next example, you'll see why that's important. Consider the problem of trying to determine if two very large files have the same contents. This is something you want to do in an operating system context all the time. So if we've computed the hash values for file 1 and file 2, first we should compare the hash values together to see if they match or don't match, because this requires constant time work, which is super fast. So if possible, we don't want to open the files at all. This would be comparing x and y directly or file 1 against file 2. But we will have to compare them byte per byte if their hash values are equal. So actually, hash functions for files are much more sophisticated than those that we use for hash tables. Instead, we use very sophisticated hashing algorithms called cryptographic hash functions and checksums. All right, another property of hash functions is that they must absolutely be deterministic. This means that if h of x produces y, then h of x must always produce y and never another value. This is super critical because this will screw up our hash table completely if this happens. We do not want this. So an example of a non-deterministic hash function is something that introduces, say, a global variable or some kind of randomness. You don't want that. So in this particular hash function, the first time I run it, the hash value for 5 is 6, but then if I call it again, we've incremented the counter and now the hash value is 7. Uh-oh, not good. Something else about hash functions is we try very hard to make them uniform. To minimize the number of hash collisions, we'll get into why hash collisions are bad shortly, but a hash collision is when two objects, x and y, hash to the same value. That is, h of x equals h of y. And the reason we want it to be uniform is so that all the values of our hash function are hit, so that we can fill the table uniformly. So for example, the table we generated earlier, William and Kate, they have a hash collision. Uh-oh. Okay, so now we're able to answer a central question about the types of keys that we're allowed to put in our hash table. We want to be uniform, so that, for example, the table we generated earlier, William and Kate, they have a hash collision. Uh-oh. Okay, so now we're able to answer a central question about the types of keys that we're allowed to put in our hash table. So what makes a key of type T hashable? Here's the answer. Since we're going to implement our hash table using these hash functions, we need those hash functions to be deterministic. And to enforce that behavior, you'll see a lot of programming languages enforce that the keys you use be immutable, meaning you can't change them. They're fixed, they're constants. So they're things like immutable strings, integers, but not things like sets or lists or things you can add or remove things from. They're immutable. And if we have that condition, and we have a hash function that is defined for all keys of type T, then we say that type is hashable. Okay. All right, so now let's get into the interesting details. How does the hash table work? Well, ideally, we want our hash function to have really quick insertion, lookup, and removal times. And remarkably, we can achieve all of that using a hash function as a way to index into a hash table. And a hash table is just a fancy word for an array. Think of it like that. Every time I say hash table, think array. So again, we use the hash function as a way to index into the hash table. So the hash function gives us an index to go look up inside the table. And yes, we can do this in constant time, given that we have a uniform hash function. Super essential. Okay, think of the hash table on the right as an indexable block of memory. So, as I said, an array. And we can access these entries with the hash function, h of x. So suppose we're going to be inserting integer string key value pairs into the table that are going to represent rankings of users to their usernames, say in an online programming competition. And this is the arbitrary hash function that we chose, x squared plus 3 mod 10. All right, let's get started. So if I want to insert the key value pair, 3 byte eater. So in the contest, the user whose username is byte eater got a rank of 3, and we want to insert that into the hash table. Then what we do is we hash the key, which is 3, and we get h of 3 being 3 squared plus 3 mod 10, or 2. So in our hash table, or array, at index 2, we're going to put the key to be 3 and the value to be byte eater. All right, now this next user, Will Fizet, which is usually what I call myself in online programming competitions, key is rank 1, and if we hash 1, then we get 4. So at index 4, then we're going to put the key in the value for William, or will.fize. Next, if we want to insert Lauren, 425, she's got rank 32. Again, we hash 32, and we put her in the table where she goes. Then we can do the same thing for Ternary Wizard, who has rank 5, and insert Orange Knight, again by hashing the key, finding out where it goes. So as we keep doing this, we keep filling the table, but eventually we're bound to have a collision. Now, in the event that we want to do a lookup for a user that has a rank R, all we need to do is compute the hash value for R and then look inside a hash table to see where this user is. So say I want to find the user with rank 10, and I hash 10, figure out its index is 3, and then I get the value, which is the Orange Knight, has rank 10. Great. However, how do we handle hash collisions? For example, users who have ranks 2 and 8 have the same value. This is problematic because we don't have another place to put them inside our table. They would index into the same position, yeah? And the answer is we use one of many hash collision resolution techniques to handle this. There are many, but the two most popular ones are separate chaining and open addressing. The idea behind separate chaining is that we deal with hash collisions by maintaining a data structure, usually a linked list, to hold
Right, looks like a lovely mod is going to sleep. Right. I think I put the volume level for the video really low because I wanted to talk over it, but I didn't fix that, so no audio in the last few minutes, but that's fine.
all the different key value pairs, which hash to some particular value. Open addressing is slightly different. And the answer is we use one of many hash collision. Orange Knight has rank 10. Great. And I hash 10, figure out its index is 3, and then I get the value, which is the Orange Knight has rank 10. Great. However, how do we handle hash collisions? For example, users who have ranks 2 and 8 have the same value. This is problematic because we don't have another place to put them inside our table. They would index into the same position, yeah? And the answer is we use one of many hash collision resolution techniques to handle this. There are many, but the two most popular ones are separate chaining and open addressing. The idea behind separate chaining is that we deal with hash collisions by maintaining a data structure, usually a linked list, to hold all the different key value pairs, which hash to some particular value. Open addressing is slightly different. It deals with hash collisions by probing and finding another place in the hash table offset from the place where we originally hashed to. So in open addressing, everything is kept inside one big array. In separate chaining, you have multiple auxiliary data structures. So the time complexity of the hash table is actually pretty remarkable. In fact, it's amazing. So on average, we can achieve constant time for insertion, removal, and search, but if you have a terrible hash function that's not uniform, then you can get linear time, which is really, really bad. All right, that's it for this video, but in the next few have a terrible hash function that's not uniform, then you can get linear time, which is really, really bad. All right, that's it for this video, but in the next few videos, we'll be going over separate chaining and open addressing and covering all of that, as well as how to remove some elements. Guys, okay, let's talk about something super, super cool, and that is hash tables and separate chaining. All right, let's dive right in. What is separate chaining? So separate chaining is just one of many, many hash collision resolution techniques. And how it works is when there's a hash collision, meaning two keys hash the same value, we need to have some sort of way of handling that within our hash table so it's still functional. Well, what separate chaining does is it maintains an auxiliary data structure to essentially hold all the collisions. And so we can go back and look up inside that bucket or that data structure of values for the
Right, I've got no idea what this guy just said. Gotta go back a little.
separate.
And how much is this? So he talks about separate chaining, open addressing, and linear probing and then quadratic probing. Double hashing, open addressing removals. Oh God. Oh God, oh God, oh God. I don't like that. I don't like that. That's a lot of videos. It's not a videos. And I also need to finish a few more data structures before I start my new position. So I am going to start learning graphs. Because I need to start learning graphs. Also, I need to do this problem. What's this? Count the number of nice nice arrays. Given an array of integers and an integer k, a continuous array is called nice if there are k odd numbers in it. 1, 2, 3. The only subarrays with 3 odd numbers are 2, 1, 2, 1 and 1, 2, 1, 1. Right. So for to have k odd numbers, it's gotta be a minimum window size of k, right? How do these guys track window sizes? I don't know. I don't know. And then I'm gonna track if there are k odd numbers in it. Right. And I equals 0. And then I'm gonna do I is less than k, I plus plus. If ik nums k is equal to nums I is nums I one, that means it's odd. So now I've got 1, 2, 3 elements here, and then I'm gonna go from int I equal to 0, I is less than insert size minus k plus 1, I plus plus. Right, if odds equal to k, well then so I form the first subarray and then I form the next one, right? Index equal to k plus I, right? And then minus k plus k. So wait, I think I'm fine with that. Right. Hmm. Interesting. Man, my legs are starting to hurt. I need to stop, but I need to take a look at how sliding windows are handled in these cases. So I'm gonna do exactly that. Along with that, I'm gonna watch a few videos of graphs because I want to start learning them. And that's gonna be awesome. Right. See you guys tomorrow. Tomorrow. See you guys tomorrow. Right. Thanks for joining in, and we're gonna do more topics tomorrow. We essentially did, well, we watched a few videos, tried the Google's OA question, which I could not solve, honest to God, and then tried doing a LeetCode question, which I could not solve. It's a really bad day, but that's fine with me. That's fine. Consistency is king. care more than anything. So I'm gonna see you guys tomorrow. Don't forget to like, share, and subscribe if you're new to the channel. And thanks for watching. Keep boys, tell me what you're doing. But the one in front of the gun lives.